Welcome to the scientific exploration of one of the most fascinating phenomena in fluid dynamics, the jetting-dripping paradox. The paradox refers to a counterintuitive behavior observed when liquid flows out of a nozzle. As you increase the flow rate, the liquid transitions from jetting to dripping, and then paradoxically back to jetting again. At low flow rates, liquid emerges as a continuous jet. As you increase the flow rate, the jet breaks up into discrete drops. But here's the paradox. Increase the flow rate even more, and the liquid returns to jetting mode. At low flow rates, we see a continuous jet of liquid emerging from the nozzle. The liquid flows smoothly in a coherent stream. At medium flow rates, the continuous jet breaks up into discrete droplets. This is the dripping regime where individual drops fall periodically from the nozzle. At high flow rates, we paradoxically return to jetting mode. The liquid once again flows as a continuous jet. This is the essence of the paradox. Increasing the speed restores the slow mode behavior. But why does this happen? What physical mechanisms drive this counterintuitive behavior? To understand this, we need to explore the underlying fluid dynamics. The key to understanding this paradox lies in a dimensionless number called the capillary number. The capillary number is defined as Ca equals mu v over sigma, where mu is the dynamic viscosity, v is the characteristic velocity, and sigma is the surface tension. The capillary number represents the ratio of viscous forces to surface tension forces. It tells us which force dominates the flow behavior. When Ca is small, surface tension dominates. The liquid wants to minimize its surface area, forming droplets rather than maintaining a jet. When Ca is large, viscous forces dominate. The momentum of the flowing liquid overcomes surface tension, maintaining a continuous jet. Let's examine the three distinct flow regimes in detail and understand the physics of each. In the first regime, at low flow rates, we observe stable jetting. In this regime, the capillary number is typically between 0.01 and 0.1. At low flow rates, inertial forces are weak. The viscosity of the liquid actually helps stabilize the jet against perturbations. Think of this like honey pouring slowly from a spoon. It forms a continuous thread because viscous forces help maintain coherence. The viscosity creates internal friction that resists the formation of instabilities, allowing the jet to remain continuous. In the second regime, at medium flow rates, we enter the dripping mode. Here, the capillary number is typically between 0.1 and 1.0. At these flow rates, a phenomenon called the Plateau Rayleigh instability becomes dominant. What is Plateau Rayleigh instability? It's a fundamental instability where a cylindrical column of liquid spontaneously breaks up into droplets. The wavelength of the fastest growing instability is lambda equals 2 pi times the square root of 2 times r naught, where r naught is the jet radius. Surface tension acts to minimize the surface area. A cylinder has more surface area than separate spheres of the same volume, so the jet breaks up. Small perturbations on the jet surface grow into waves. These waves eventually pinch off, creating discrete droplets. Think of water flowing from a faucet at medium speed. You can see the continuous stream break up into individual drops as it falls. Now we come to the paradoxical third regime at high flow rates. In this regime, the capillary number exceeds 1.0. At high flow rates, inertial forces become so strong that they actually suppress the Plateau Rayleigh instability. The jet is moving so fast that surface tension doesn't have enough time to act and break it up before the liquid has traveled far downstream. Think of a fire hose shooting water at high pressure. The water comes out as a powerful jet, not as droplets, because the momentum is so high. The high momentum of the liquid overpowers surface tension effects, maintaining jet coherence. Let's dig deeper into the physics that governs these transitions. Another important dimensionless number is the Weber number. The Weber number is defined as V equals Rho v squared L over sigma, where Rho is density, v is velocity, L is characteristic length, and sigma is surface tension. The Weber number represents the ratio of inertial forces to surface tension forces. The Weber number is related to the capillary number and Reynolds number by V equals Ca times Re. The transitions between regimes occur when the Weber number crosses certain threshold values. Let's work through some numerical estimates using water as our example fluid. For water at room temperature, we have the following properties. The dynamic viscosity mu is approximately 0.001 Pascal seconds. The surface tension sigma is approximately 0.072 newtons per meter. The density ρ is 1,000 kilograms per cubic meter. Let's consider a nozzle with an inner diameter of 1 millimeter. For the low flow rate jetting regime, let's say the velocity is 0.1 meters per second. The capillary number is 0.001 times 0.1 divided by 0.072, which equals approximately 0.0014. This low capillary number corresponds to stable jetting in the viscous-dominated regime. For the dripping regime, let's increase the velocity to 0.5 meters per second. Now the capillary number is approximately 0.0069. The Weber number is 1,000 times 0.5 squared times 0.001 divided by 0.072, which gives us approximately 3.47. This Weber number is in the range where Plateau Rayleigh instability causes the jet to break up into droplets. For the high flow rate jetting regime, let's push the velocity to 5 meters per second. The capillary number is now approximately 0.069. The Weber number jumps to approximately 347. At this high Weber number, inertial forces completely dominate, suppressing the instability and restoring jetting behavior. Another way to understand the paradox is through competing timescales. There are three important timescales that govern this phenomenon. The capillary timescale T-cap equals the square root of RHOR cubed over sigma. This is how long surface tension takes to act. The flow timescale T-flow equals L over V. This is how long the liquid takes to traverse a given distance. The viscous timescale T-visc equals RHOR squared over mu. This characterizes viscous diffusion. In the dripping regime, the capillary timescale is shorter than the flow timescale. Surface tension has time to act and break up the jet. In the high-speed jetting regime, the flow timescale becomes shorter than the capillary timescale. The liquid moves away before surface tension can break it up. A key question is, what exactly determines the transition points between these regimes? The answer is that the critical values depend on the nozzle geometry, liquid properties, and the precise flow conditions. For typical cylindrical nozzles, the first transition occurs around Weber number equals 1, and the second transition around Weber number equals 100. This paradox isn't just academic curiosity. It has important real-world applications. Inkjet printing relies on controlled droplet formation. Understanding the jetting-dripping transition helps optimize print quality. In engines, fuel injectors must atomize fuel efficiently. The regime depends on injection pressure and nozzle design. Industrial spray coating needs uniform droplet size. Operating conditions are chosen based on these fluid dynamics principles. Medical nebulizers and drug delivery systems use these principles to create droplets of specific sizes for optimal absorption. From inkjet printers to fuel injectors, the jetting-dripping paradox influences countless technologies. Experimental studies have revealed fascinating details about these transitions. High-speed camera studies show that the transitions exhibit hysteresis. The transition points differ depending on whether you're increasing or decreasing the flow rate. During the dripping regime, researchers observe satellite droplets. These are small secondary droplets that form between the main drops. Why do satellite droplets form? When a droplet pinches off, it leaves behind a thin liquid thread that also breaks up into tiny droplets. The liquid bridge connecting the main drop to the nozzle breaks up, creating these satellite droplets. Modern theoretical models provide deeper insight into the paradox. The complete description requires solving the Navier-Stokes equations with free surface boundary conditions. The Navier-Stokes equation states that rho dV over dt equals negative gradient P plus mu del squared V plus rho G. Linear stability analysis of the jet can predict the wavelength of the fastest growing instability. The growth rate omega squared equals sigma k over rho h r naught times the quantity 1 minus k squared r naught squared, where k is the wave number. The maximum growth rate occurs at a specific wave number that determines the droplet size. Modern computational fluid dynamics simulations reveal the complex, three-dimensional dynamics of the transitions. The nozzle geometry significantly affects the transition behavior. Sharp-edged nozzles tend to promote earlier breakup because they create flow separation and vorticity at the nozzle exit. Rounded or contoured nozzles can extend the jetting regime to higher flow rates by providing smoother flow acceleration. Compare a sharp-edged nozzle on the left with a rounded nozzle on the right. The geometry dramatically affects the flow behavior. Different liquid properties also modify the paradox behavior. Higher viscosity liquids maintain jetting at lower flow rates because viscous damping suppresses instabilities. Higher surface tension promotes dripping by making the capillary forces stronger relative to inertia. Liquid density affects the inertial forces, with denser liquids requiring higher velocities to achieve the same Weber number. Let's compare glycerin with water. Glycerin has a viscosity about 1,000 times higher than water. Glycerin's viscosity is approximately 1 pascal second. At the same velocity of 0.1 meters per second, the capillary number for glycerin is about 1.6. This means glycerin will remain in jetting mode at much lower speeds than water due to its high viscosity. For vertically falling jets, gravity also plays a role through the Bond number. The Bond number is defined as BO equals RHO-GL squared over sigma. The Bond number compares gravitational forces to surface tension forces. For small nozzles, the Bond number is typically small, meaning gravity effects are negligible compared to surface tension. For large nozzles or very slow flows, gravity can become important and modify the transition behavior. Despite extensive research, some aspects of the paradox remain incompletely understood. The exact transition boundaries can vary significantly with experimental conditions like ambient pressure and temperature. Three-dimensional effects, especially near the nozzle exit, are not fully characterized in all flow regimes. Non-Newtonian fluids, like polymer solutions, show qualitatively different behavior that's still being investigated. An interesting question is, can we design a nozzle that eliminates the dripping regime entirely, going directly from low-speed jetting to high-speed jetting? The answer is possibly yes, using active flow control or specially designed nozzle geometries that suppress the Plateau Rayleigh instability. Let's discuss the practical implications of this paradox for engineering applications. A key design principle is to choose flow rates that avoid the dripping regime if you need consistent behavior. Conversely, if you want to generate uniform droplets, you should operate precisely in the dripping regime. The flow rate must be carefully matched to the nozzle diameter to achieve the desired regime. A typical regime map shows jetting at low flow rates, dripping at medium rates, and jetting again at high rates. We can also understand the paradox from an energy perspective. Surface energy considerations drive droplet formation, because droplets minimize surface area for a given volume. The surface energy equals sigma times the surface area A. Kinetic energy of the flowing liquid maintains jet coherence by providing momentum that resists breakup. The kinetic energy equals 1/2 rho v squared times the volume. The transition back to jetting occurs when the kinetic energy becomes large enough to dominate over surface energy considerations. An interesting extension is the behavior of coaxial jets, where one liquid flows inside another. Gas-liquid coaxial jets show similar paradoxical behavior, but with additional complexity from the interaction between the two fluids. Both the inner jet velocity and the outer jet velocity affect the regime transitions. In a coaxial configuration, we have an inner liquid jet surrounded by an outer liquid or gas stream. Let's briefly discuss the historical context of this discovery. The jetting-dripping paradox was first observed systematically in the 1980s using high-speed photography. Planet and Hysteresis provided key theoretical insights in a 1999 paper that explained the mechanism behind the paradox. It remains an active area of research, with new discoveries being made about complex fluids and microfluidic applications. Let's look at the mathematical framework for stability analysis. The analysis begins by perturbing the cylindrical jet surface with small sinusoidal disturbances. The perturbed radius is r of theta zt equals r naught plus epsilon times e to the ikz plus omega t. The growth rate omega determines whether perturbations grow or decay. Positive omega means instability. The growth rate omega depends on viscosity mu, surface tension sigma, density rho, velocity v, and wave number k. Dimensionless analysis reduces this complex parameter space to just a few key dimensionless groups like the capillary number and Weber number. The paradox has important implications for microfluidic devices. At the microscale, surface tension effects become more important because the bond number decreases. Precise control of droplet size in lab-on-a-chip devices requires a detailed understanding of these regime transitions. Many microfluidic droplet generators intentionally operate in the dripping regime to produce monodispersed droplets. Microfluidic channels can generate highly uniform droplets by carefully controlling the flow rate in the dripping regime. Temperature can also affect the jetting-dripping transitions. For most liquids, viscosity decreases exponentially with increasing temperature. Viscosity as a function of temperature approximately follows mu of T equals mu naught times E to the negative beta T. Surface tension also decreases with temperature, though more gradually. By controlling temperature, we can shift the regime boundaries and optimize the flow behavior. Let me summarize the key concepts we've covered about the jetting-dripping paradox. The paradox is that increasing the flow rate causes a transition from jetting to dripping and then back to jetting. The capillary number and Weber number are the key dimensionless parameters that govern these transitions. At low capillary number, viscous forces stabilize the jet. At medium values, the Plateau Rayleigh instability causes the jet to break up into drops. At high Weber number, inertial forces suppress the instability and restore jetting. The applications range from inkjet printing to fuel injection systems. The jetting-dripping paradox beautifully illustrates the complex interplay of forces in fluid dynamics. It demonstrates that our everyday intuition can be misleading when dealing with the subtle balance of forces in fluid mechanics. Proper understanding requires careful dimensionless analysis to identify the governing parameters. This paradox continues to inspire both fundamental research and practical innovations in fluid control.